and your non-metal would be the one that would gain electrons. See, we did all these types of chemical bonding. We did dot and cross diagrams, um, and last time I gave you these questions as well. So we started talking about. So what happens in ionic bonding is that you have a metal and you have a non-metal, and the metal loses its outer shell electrons, and the non-metal gains its outer shell electrons and gets a complete outer shell at the end. And whatever charges they're going to get by doing that, you have to balance the number of electrons lost and gained. So the simple rule is you have to multiply the atoms by a certain number. And the easy way to find that out is that if this is -2, then you multiply this by 2. And vice versa, if this is +3, you multiply this by 3. So we did all of this, and we started talking about the physical properties of ionic compounds. Physical properties work. The first thing that we talked about when we were talking about physical properties was we started talking about the giant ionic lattice, that they have a giant structure. Focus on the word giant. It's that means it's a endless. It's a very big structure. It's a regular arrangement of oppositely charged ions. So whenever you have positive and negative ions, so there's not going to be just one positive and one negative ion. There's going to be lots of positive and negative ions all attracted to each other. There's going to be strong forces of attraction. So I also explained that ionic compounds are represented by formula units. Like if this is lithium and this is fluorine, the ratio in which they exist, the formula tells you, or the dot and cross diagram tells you the ratio in which the two ions would exist. For example, in this case, this is one lithium and this is one fluorine. So that means that for every one lithium, there's going to be one fluorine. For every one lithium losing one electron, there's going to be one fluorine that would be gaining one electron. So in reality, there would be a lot more lithiums and a lot more fluorines. There would be hundreds or thousands of lithiums and fluorines. So the ionic dot and cross diagram, it gives you the simplest ratio in which the ions exist. And so the second point that we discussed was high melting points. We discussed that some of them have really high melting points. The ionic bonds, they vary. I told you that you can have a stronger ionic lattice if you've got greater charge. So Mg is +2, O is -2. So the attraction would be a lot stronger. So we did examples for that. Now the next property that we're going to talk about is solubility and the electrical conductivity of ionic compounds. Okay, so let's talk about solubility first. So that's going to be our third property. So property number 3. So that's the property number 3 is solubility. Now what happens? What happens in solubility? That ionic compounds are usually soluble. So they're usually soluble, and solubility varies. So at least the solubility is going to vary. So for example, you have chalk. That's an ionic compound that's not very soluble. So it has a lower solubility. While you have your normal table salt, which is sodium chloride. So that one is very, very soluble. So what happens when you mix an ionic compound in water? What happens when you stir a table salt, when you stir table salt, a spoonful of table salt into water. So what's going to happen is, like if you have NaCl, now NaCl would have, it's going to have sodium ions and it's going to have Cl ions. So here's our sodium. So let's say I have these four particles, and it's a tiny crystal. So I've got my sodium ions and my Cl ions, and they're all attracted to each other. They're forming this tiny crystal. ठीक है Saneem, I'll send you the recording. Is the voice clear for everyone else?
Yes, sir.
Acha. So this one, let's assume this is the tiny crystal. This is a grain of salt. There's a sodium ion attracted to a Cl ion, which is attracted to a sodium ion back again, and it's attracted to a Cl ion. So there's this crystal, and I'm going to try and dissolve it in water. So I'm going to mix it in water. So here's a bowl that's full of water. Now what happens over here is that when I mix normal table salt, a crystal of table salt, in water, what happens is that the salt particles or the ionic compound, it would dissociate. What that means is that when I vigorously stir, all the ions are at the moment attracted to each other. But when I vigorously stir, what happens is that the ions, they scatter. Okay? Imagine that I'm vigorously stirring. So all these ions, they're going to scatter. So sodium ions would travel to this side. So they would dissociate. This is known as the ionic compound dissociating. Is this clear?
Yes, sir.
ठीक है आपने, is this clear?
Yes, sir.
So vigorous stirring, your ionic compound dissociates. Now, when it does that, when the ionic compound dissociate because of vigorous stirring, the ions are no longer able to get back together again. The ions are a lot smaller, so let me just make them smaller. Now, when you mix NaCl, normal table salt, in water, you never see the crystal back again. Like if the white crystal that you mix in water, it is gone forever until and unless you get rid of the water. And the reason for that is that there's a lots of water molecules that are in between them, which will not allow them to get back together again. Like even if the sodium ions and Cl ions are attracting each other, there's so many billions of these water molecules that are in between that they don't allow the ions to get back together again. So which is why once you dissolve NaCl, it kind of remains dissolved for almost forever. So this is what's going to happen when you have NaCl solid. You dissolve it, and when you mix them together, the sodium ions dissociate from the Cl ions, and the ions, they become separate. So the ions are no longer together, but they are separate from each other. ठीक है, is this clear? Turhan, is this clear?
Yes.
So yes, acha. So NaCl dissociates, dissolves, and it dissolves into aqueous ions. So remember this. This always happens when you mix any salt crystal. The salt crystal would, its ions would just scatter in water, and the ions are going to completely dissociate. And this applies to all ionic compounds. Now, for some, it's very easy to dissociate, but for others, where the ionic bond is really strong, for example, if the ions are really attracting each other very strongly, no matter how vigorously you stir, the ions don't dissociate. They don't scatter. Marble is one example. Like you put a piece of marble into water, Because the ions are so strongly attracted to each other, no matter how fast you stir it, nothing would happen. It's not going to dissociate a lot. There's just going to be a very little amount of dissociation. So the solubility is going to be a lot less. So this is how ionic compounds look like when they're dissolved in water. Um, Now moving to the fourth point. TK, remember the dissociation part. TK, that's going to be helpful later on as well. Just remember, in aqueous state is a state when they're mixed with water. So in aqueous state, ionic compounds are always in their dissociated form. They're no longer together. You're not supposed to write NaCl together now, because the Na and the Cl lines are now separate from each other. I said now the fourth point is that they're good electrical conductors. NaCl or ionic compounds, they conduct electricity, but only in certain cases. So they're going to conduct electricity in molten and aqueous state only. Otherwise, they're not no electricity conduction in solid state. And the reason for that is that first thing is, what is electricity? Electricity is the movement of charges. So when we say that that a wire has a current in it, so that's basically charges moving in the wire. So it's the movement of charged particles. So in ionic compounds, you do have charged particles, but in solid state, they can't really move around. They're all stuck in place. Okay, so for example, you have this ionic lattice. The charged particles cannot move around. They can't really travel. So in solid state, the ionic compound is not going to conduct electricity. So ionic compounds, they only conduct electricity in molten or aqueous state. And if you're being asked why it doesn't conduct electricity in solid state, you're going to write it has no free moving ions, because all the ions are stuck in their place. Or vice versa, why do they conduct electricity in molten or aqueous state? Because in molten state or aqueous state, like the state that I showed you over here, the ions can freely move around. So the answer to this part would be that you've got free moving ions. So the ions can sort of move around. Is this clear? ठीक है,
Yes, yes.
okay. So the ions in this case they can move around. So those are all the properties of ionic compounds. Four properties. They've got giant ionic lattices. We can talk about a fifth property, and that fifth property is that they are brittle, crystalline solids, or crystalline lattice. So focus on the word brittle. What does brittle mean? Brittle means that they can break, they can shatter if you apply a force. So they can kind of break and shatter when a force is applied. Uh, Now a lot of things, they don't break. Like if you, I mean, wood is one example. Like it would bend, metals would bend. A lot of things around you, they don't break when you apply a force. Uh, I mean, they get D-shaped. But with ionic crystals, the thing is that if you apply a force, and ionic lattices can be very strong. For example, marble is very strong. If you've got a marble tile, that's kind of pretty strong. Cement is very strong. All the concrete around you, that's an ionic lattice. That's very strong. So they can be very strong, but when you apply enough force, they're going to resist the force to a certain extent. But at a very certain point, all of a sudden, they don't get D-shaped. They don't get. I mean, the shape doesn't change. It just cracks. It completely cracks and shatters. That is how ionic lattices behave. Unlike if you apply a force to a metal, it would bend. If you apply a force to almost any other thing, it would get D-shaped. It would get deformed. But not ionic lattices. They would resist completely. For example, there's a tile. It's nothing would happen to it. But at a certain point, if enough force is applied, all of a sudden it's going to break and break into pieces. So, so the question is, why do ionic compounds behave this way? Even though they are kind of very strong, but at a very certain instant, why do they completely shatter? So that's the question. That they can be very strong, but at the same time, they can be very brittle as well. So the answer to that is because their structure is has some issues. So let's say here's my ionic lattice, and it's got positive and negative ions all alternatively arranged. So let me just mark the positive and negative ions. So positive attracting negative, negative attracting positive, and so on. So I've got all my positive and negative ions, and we can just increase the size of the lattice. So what's going to happen is when you apply a force, and let me make another row. So this is a crystal. So when you apply a force, the ions are really tightly held together, so nothing happens to it. All the positive and negative ions are attracted to each other. But when you apply a force beyond a certain point, like there's a marble tile and you apply too much force, when you apply too much force, the lattice would all of a sudden start to slide. It's going to get D-shaped, or it would slide for a very minor instant. And this should not happen. Because if this happens, what's going on now? That if it slides, if the lattice slides and you're applying this force, the two negative ions are now adjacent to each other. Two positive ions are also adjacent to each other. I mean, previously there was a force of attraction. Oppositely charged ions, they attract each other. So previously in its original form, they're all attracted to each other. Like positive attracts negative, negative attracts positive, and so on. But when you apply a force and you apply too much force, then the lattice might just slide a little bit. Is this idea clear? You
Yes,
clear?
sir.
Achha, so all of a sudden now, that force of attraction, that same force of attraction, has now turned into a force of repulsion because you were not supposed to have two negative ions together, and you're not supposed to have two positive ions together because they're going to repel each other. So this is the crack that's appearing, and the crack would just continue. It's going to be like if you have a tile and you're trying to chip it at this point, then and you hammer it over here. Now the crack would not just appear over here; it's going to just go on, and it's going to break the whole structure. Is this idea clear?
Yes, sir.
Okay, is this clear to everyone?
Yes, sir.
Okay, so just remember this point that ionic lattices can be very very brittle. So that pretty much ends ionic compounds. Just remember how to draw the dot and cross diagrams. We're going to move forward with so we are going to move forward with covalent bonding now. So the question is, what is covalent bonding? Now that's a completely different thing compared to ionic bonding, and we're talking about simple molecules over here. So just a brief introduction first. Now in ionic bonding, you had an atom X and you had an atom Y. Now what was going on in ionic bonding? In ionic bonding, if you had electrons, right, then one of the atoms had a very strong tendency to gain electrons. So it would pull the electrons from one of the atoms and it would gain it, right? So one of the atoms had this very, very strong tendency to gain electrons. Now in covalent, what would happen is that you would have two non-metals bonding to each other. And we know that non-metals, they like to gain electrons. So they like to gain electrons. So let's say you have an atom X and you have an atom Y, and there's an electron over here. Now both of them are trying to gain electrons. Like Y is trying to pull electrons to itself, and X is also trying to pull electrons towards itself. Where do you think would the electron end up? Would it go to the right, or would it go to the left, or would it stay right in the middle? क्या होगा?
It would stay in the middle.
ठीक है.
In the middle.
ठीक है, it would stay in the middle. This is called sharing of electrons. So in covalent, what happens is that since both of the atoms are non-metals, in ionic it was the opposite. In ionic, you had a metal and you had a non-metal. So the metal actually metal wanted to lose electrons. So the electrons went to the non-metal, right? But in covalent, both of the atoms are going to be metal atoms. And whether it's non-metal atom X or non-metal atom Y, they both are going to try and gain electrons, and the electrons would get stuck in the middle. Okay, just like a tug of war, the electrons would get stuck in the middle and they wouldn't be able to go anywhere. That's sharing of electrons. So we're going to do the first one. Let's draw HCl. So now in HCl, both of them are non-metals. Both of them would try to gain electrons. So here's my Cl. In covalent, you usually just draw the outer shell electrons. So Cl over here has a total of how many electrons? It's going to have a total of 7 electrons. It's in group 7. And you've got H over here. H has a total of electrons. It just has 1 electron. So H has exactly 1 electron. That's it. Now, what's going to happen is they're both going to try and pull each other's electrons. Like Cl wants 1 electron. So Cl sees hydrogen's electrons, it would try to gain that electron. H also needs 1 electron, so it would see Cl's electron, it would try to gain that electron. What's eventually going to happen is that Cl wants 1 electron, so Cl would try to pull the electron, but not only the whole atom would get dragged along because the H is not willing to lose that electron. And that's how a covalent bond is formed. Like Cl wanted 1 electron, right? So Cl pulled hydrogen electron, tried to gain it. But the whole hydrogen wasn't willing to lose that electron because they both like to gain electrons. So the whole entire hydrogen atom would come and bond with it, and the electrons would be stuck in the middle. And that's known as your covalent bond. Is this clear?
Yes, sir.
Just similarly, we can do another example. Let's do an oxygen molecule. Now in oxygen, you've got 2 oxygen atoms. Oxygen again is a non-metal, so it would obviously try to gain electrons. But the other atom is also oxygen. So you have an oxygen, and it's got 6 electrons in its outer shell. And here's another oxygen which has 6 electrons in its in its outer shell. Now, this oxygen over here needs 2 electrons. So what it would do is it's going to try and pull the other oxygen's 2 electrons towards itself. But the other oxygen is not willing to lose those electrons. So the whole oxygen atom would come and would start forming covalent bonds. And as a result, you would have this is known as a double covalent bond. So that's our double covalent bond, because now it's 2 electrons each being shared. Is this clear as well?
Yes, sir.
Yes, sir.
So drawing molecules like this can be a bit tedious because or confusing at times. For example, if I want to draw oxygen with let's say fluorine. Now oxygen is in group 6. So oxygen is over here. It's got 6 electrons. Somebody tell me how many electrons does it need?
2.
It needs 2 electrons. So if I have fluorine on the other hand, so this fluorine atom would have 7 electrons. So oxygen sees fluorine and would try to pull 1 electron from fluorine. So that's a single covalent bond. And as a result, fluorine wanted 1 electron as well. So oxygen, it pulled 1 electron from oxygen. So 2 electrons are stuck in the middle. Now in this case, fluorine's outer 8 electrons are complete because it got 1 electron from oxygen. But oxygen, on the other hand, its outer shells are not complete. It still needs one more fluorine. So there's going to be one more fluorine atom. And you would have the oxygen would try to pull fluorine's electrons. And they're going to gain those, oxygen would be able to gain those electrons from fluorine, and oxygen's 8 electrons are complete. So is the idea clear behind covalent bonding?
Yes, sir.
Yes, sir.
I said next one. Okay. Now the whole problem is that it's kind of really difficult to actually draw these dot and cross diagrams. Because especially for covalent molecules, because you can get them wrong, so you have to do them over and over again. One thing is just make sure that after the covalent bonding, does each atom have 8 electrons? Do they have a complete octet or not? I mean, oxygen got 8 electrons. Fluorine got 8 electrons. This fluorine over here is also now has 8 electrons. Now, one easy method for that is that you should know how many bonds does each atom form. So we can make a table and we can make this easy now. And that is that if you're a group 7 atom, remember that it forms one bond only. Why does it form one bond? Because it only needs 1 electron. If you're a group 6 atom, then you're going to make 2 bonds. Because in group 6 you have 6 electrons and it's in your outer shell, and you just need 2 electrons. So then if you're a group 5 atom, you're going to make 3 bonds. And if you are a group 4 atom, you're going to make 4 bonds. So basically, if you need 1 electron to complete your outer shell, you're gonna make 1 bond. If you're in group 6 and you have 6 valence electrons in your outer shell, you need 2 electrons. So you're going to make 2 bonds. Group 5 will have 5 electrons in their outermost shell. And if you have 5 electrons in your outermost shell, you need 3 electrons. So you're going to make 3 bonds. Okay, is this clear?
Yes, sir.
Yes, sir.
Anyways, I'm going to continue with this thing in a lot more detail in the next class, probably. Right now, just make sure what covalent bonding is. That in covalent bonding, both of them are nonmetals and both of them try to gain electrons. So the electrons kind of get stuck in the middle. And there's going to be a force of attraction. The nucleus of this atom would be attracted to electrons, and the electrons would be attracted to the nucleus. So all three are attracted to each other. Uh, Sometimes an atom has to gain two electrons to complete its outer shell. Sometimes it just needs to gain one electron to complete its outer shell. So the rule is a group 7 atom would always make one bond, group 6 atom would always make two bonds, and so on. Group 5 will make three, and 4 will make four bonds. Is this clear?
Yes, sir.
Yes, sir.
So we're going to continue in a lot more detail in the next class then, okay?
Okay, sir. Allah Hafiz, sir.
Okay, I have to go somewhere. So we'll discuss this in a lot more detail in the next class then. Okay, Allah Hafiz.
Allah Hafiz, sir.
Hafiz.